Now we're going to do a couple more interesting examples using the limit comparison test. These will require a little bit more of you, but not so much more. So the first one is sine of 1 over n cubed from n equals 1 to infinity. Now the question becomes, what do I compare this to? And in this particular case, you might ask yourself, okay, well wait, hold on, sine isn't always positive. That's so you can't use the limit comparison test. And that is true. Sine is not always positive. But if you start at n equals 1, and so then that sine of 1, and then you get larger and larger, that 1 over n cubed drives down to 0 but never quite gets there. So if you look at 1 in radians, that's going to be in the first quadrant, because the first quadrant goes up to about 1.5, 1.6 radians. And so since it goes, so you start in the first quadrant and you work your way down. So this, if you plot this out, you'll find this is actually it is positive the entire time. So then, okay, all right, that's great. What do I compare this to? Well, if you've got nothing better to do, then why don't you compare it to something like 1 over n cubed? It's like, well, I mean, why would I do that? Well, you know, there's reasons. Part of that is that old sine x over x. If you remember that, that's sine of x over x as x goes to 0 is 1. So sine 1 over x over 1 over x as x goes to infinity turns out to be pretty good estimate. So when you have sine of something, choosing to compare it to something is okay. If you're going to infinity, 1 over is okay. If you're going towards 0, compare it to the exact same thing also. Anyway, it's just a good starting position, and we'll see why. So I want to take the limit as n goes to infinity sine of 1 over n cubed over 1 over n cubed, which is not that helpful. If you take n out to infinity, well, that becomes 1 over a big number, so that's 0. Sine of 0 is 0. 1 over a big number, that's 0. So I have 0 on top and I have 0 on bottom. That's kind of ideal for the L'Hopital's rule. So what we got to do is we got to take the derivative of top and the derivative of the bottom. So what we're really doing is the derivative of the top is cosine of 1 over n cubed times the derivative of 1 over n cubed. And on bottom, we're taking the derivative of 1 over n cubed. So we really don't have to take those derivatives because we know that those two things are going to be the same. So what we really have is the limit as n goes to infinity of cosine 1 over n cubed. Now as n gets large, 1 over n gets really small. So that gets me cosine of 0, and cosine of 0 is 1. So since cosine of 0 is 1, we know that these two have the same convergence value. So what I have to do is I have to say, okay, well, what's the convergence of that? Well, this is a p-series. It's 1 over n to a power. So I look at p. P is 3, and 3 is greater than 1. So I know it converges. So I know that series converges, which is not that difficult. You just had to, the trick was picking what that was going to be, which is not always intuitively obvious. Now this one over here is going to require a little more tinkering. I have 1 over n plus 1 times natural log of n. Okay, so to do that, what I need to do is I need to say, okay, what do I compare this to? In my mind, the natural thing is to take when you have these polynomials, you always want to shrink them. So I have an n plus 1. I don't want n plus 1. What I'd like is 1 over n natural log n. Now the question is this going to be a good comparison? It might not be. But you have to run it to at least figure it out. And you're not always going to be good at this the first few times. It takes practice to develop that intuition. So I'm going to take the limit as n goes to infinity, 1 over n plus 1 natural log n over 1 over n natural log n. Now, of course, we're going to rewrite this because that's disgusting. So we're going to rewrite that as n natural log n over n plus 1 natural log n. Now that's going to make our lives easier because we can actually cancel the natural logs at this point. Just cancel them out. So then what we're really looking at is the limit as n goes to infinity of n over n plus 1. Well, hopefully you can perform that limit and you can easily get that that's going to be 1. Not a problem. Now the question becomes, we have to find the value of that series and say, okay, well, does this converge or diverge? And you also can't start at n equals 1. The reason you can't start at n equals 1 is because that natural log of 1 is 0. It's going to blow up there. So we need to start at 2. And that's okay. We can do is we can take... What do we do here? Well, actually applying the integral test is a good candidate. I have this because it's not a p-series, and you can't really look at it like a p-series, and direct comparison is not going to help you here. You could get it using a certain direct comparison, but you're not guaranteed that's going to converge. So the key to doing this is going to be taking the integral test to figure this one out. This is why this becomes interesting, is that you can't just immediately figure out what the convergence or divergence of this is. So I have to say, all right, what's my integral 2 to infinity of 1 over x natural log x dx? Now, one thing we have to remember with the integral test is that this always has to be positive and decreasing. And it turns out it is. You'd say, all right, f of x is 1 over x natural log x. So f prime is negative 1 x natural log x to the negative 2 times 1 plus 1 over x, or 1 plus natural log x, sorry. And so this is going to be something squared, so it's always positive. Natural log is positive for any value greater than 1. And you have a negative, so positive times a negative, so it's decreasing for all values of x greater than or equal to 2. Actually, technically greater than 1, but so we know that this is positive because this is always positive for values greater than 1. This is decreasing. It's positive, decreasing, so we satisfy the values for the integral test. So now these are going to converge and diverge together. So they're, you kind of have that old equivalent thing like in geometry or whatever. But anyway, it doesn't matter. So how do I find that integral? Well, what you're going to have to do is you're going to have to use a substitution. You're going to say, all right, u is natural log x. So du is 1 over x dx. So now I have an integral from natural log 2 to infinity of 1 over u du. Alright, well I can take the antiderivative here. I get the natural log of u from natural log of 2 to infinity. Now I could do this in x. If I converted back to x, it would actually be the natural log of x from 2 to infinity. If I plug infinity in for x, I get infinity. Natural log of infinity is infinity, so I mean, right, it's natural log of a big number is a big number. Natural log of that is still a very big number. So this limit goes out to infinity, it blows apart. Right, this is an improper integral. You have to take, the appropriate limits and whatnot. So it doesn't matter when you evaluate it at the lower limit. It doesn't matter because natural log of natural log 2 is finite. Who cares? But this is infinite, so it blows out. That tells me ultimately diverges. Right, that's a lot of work to get diverges, but ultimately it shows that the limit comparison test is powerful, but it may not be the only tool you have to apply.